Okay, we're continuing on. We're continuing on in exam 3. This is page 2, which is kind of more of the same of page 1. Again, it's just asking us to fill in the blanks to complete the reactions in the best way possible. We may not have to use everything there. Or excuse me, we may not have to use every blank. So let's take a look at the first one here. Not much is given. It just says that we're going to end up making an alkane at the end. Okay, and there's only one reaction that we know of so far that can turn anything into an alkane. We know that we're in chapter 6, so we know we have to start with an alkene, right? That's all we know so far, so we know we have to do an alkene into an alkane, and there's only one reaction that we know of how to do that, and that's our hydrogenation, right? So hydrogenation. And that is simply where we have H2. Sorry, let me write that a little bit neater. Where we have H2, and we have some kind of catalyst. We'll pick nickel, right, today. That should be just fine. And so then we just find a double bond somewhere on this ring. Again, it doesn't matter where that double bond is, just a double bond somewhere on that ring. Okay? Good. All right. Here we have another example of a hydrohalogenation. Again, we're adding H and Cl. Again, we differentiate between the two carbons in the alkene. The red is being tertiary, the black being secondary. So we are just going to be adding the Cl to the more substituted side. Okay, here we have BH3, and then we have some peroxide, sodium hydroxide, and water. This is our hydroboration. So hydroboration, oxidation. And hydroboration oxidation adds H and an OH. It adds the OH anti-Markovnikov. So the OH gets added to the less substituted carbon. And it is a syn addition, right? So it's a syn addition of the H and the OH. Okay, so we find our double bond. We identify the more and the less substituted carbon. So in this case, since it is a hydroboration oxidation, and we know that this is anti-Markovnikov addition, we are going to add our OH to the less substituted side. So let's draw our rings. Okay, there's our methyl group. Let's just put a color in there so we can identify what we're doing. Right, so there's our methyl group there in green. There's our red. There's our black. Right, and so it's a syn addition of the H and the OH. And so if we want to fill in all the blanks, right, there's that. And then we can just connect. I missed a little bit there. Okay, right, we can just connect the other piece. Okay, so there's one of the answers we can have, or, right, you can just go ahead and add the other version, right, where let's add the OH and the H, right, and then we have our green methyl group tucked away in the back there, and there's that. So either one of those, or I should say both of those, would be the answers for this problem. Okay. Here again, for the next problem, we see a syn diol, right? The two OHs are added to the same side. So this is, again, just another example of osmium tetroxide at work. It doesn't matter if we're on a ring, right? It's not really going to change anything for us yet, right? We are just changing an alkene into a syn diol. All right, now we come across to a different kind of a setup, a different problem here a little bit, right? Remember that squiggly bond just means an ambiguous stereochemistry. We have both wedge and dash being present there, right? That's another way of interpreting that. Now, what do we notice about this double bond? All right, so now we got to pause for just a second. We got our red, we got our black carbons. Both of those are secondary. Now, next door to those secondary, we have tertiary positions, right? Let's mark those green, right? So next door to our red and our black carbons, we have those green carbons. So if we generated a carbocation, okay, if we generated a carbocation as we were going through our reaction, right, we would see some shifts occur. Okay? So we would see some shifts occur to get to the green carbons. So what I mean is, if we use an acid, such as acid catalyzed hydration, right, if we generate a carbocation, we would shift where the OH would be added to the green carbons rather than the red or to the black. So we need to do a hydration, right, because we're adding H and OH, okay? What I don't show here, right, is that we had to add another H to that other carbon. It's not explicitly shown, I should say. So we have to add the OH and the H. So we have to do a hydration with no cation, right? No cation / shifting. And there's only one thing that we know of so far that can accomplish that. And so I think the choice that might have been most often is our oxymercuration. So, and then our demercuration. Okay. Or you could have done a hydroboration oxidation here too. Right? I know there's some steric effects to both of these problems, but it's not something we're kind of covering for this semester at the moment, right? So both of those would have been valid answers in this case. The key part is understanding this, right? Next door to those two red and black carbons, there's a tertiary position, so we have to shut down any potential shifts or carbocation formation. So we have to use the right conditions not to generate those carbocations. So either hydroboration oxidation or the oxymercuration would have worked in this case. So let me just zoom out. There's the answers that I had for this and the notes that I took along with it. So if you guys want to pause, take a look at this. In the next video, we'll pick up on page 3.